In graph searching, there are two variants, that is breadth first, BFS, and DFS. Breadth first transversal uses your Q data structure, and DFS uses stack. We are now, for the sake of simplicity, we are using your recursive stack, that is inbuilt stack. Recursion हम use करेंगे यहाँ पर. So they use for transversal purpose. That means if I want to print all the node values of a graph, I can take the help of either of these transversal. This is also called search. Search reason being, if I want to search for a path from A to say destination some D, then this will give me a path of, or shortest path, whatsoever you want to do depending on the application. You can explore that path till that node. In general case, if I want to do traversal, then you will have to explore or visit every node of the graph exactly once. So that depends upon your choice, whether you want to say I need the path from, say some node is there, say D is there, some intermediate nodes are there. I can start from source vertex and stop at destination vertex. That is only for searching purpose. If I want to explore all the nodes, then I will have to, I can't stop in between. I have to explore all the possible vertices in the graph. BFS explores all the adjacent to in the parallel nature. तो explore all the edges in parallel. तो discover करती हैं उसको parallel, which are reachable. सबसे बड़ी application BFS की क्या है? If I want to know कि कोई भी starting vertex है, वहां से आप traversal शुरू कर सकते हो, traverse कर सकते हो. It basically tells you what nodes are reachable from R. तो R से कितनी nodes reachable है? Luckily इस ग्राफ के अंदर सारी की सारी नोड reachable हैं. तो which nodes are reachable from R if I want to know, कि अगर मुझे कहीं, अगर मैं कोई प्रोजेक्ट बना रही हूँ, I want to say यहाँ से मुझे एक डाटा डिलीवर करना है, कहते हैं जी यहाँ से लेके कोई भी आप पाथ के थ्रू जाओ, क्या यहाँ पर डाटा डिलीवर कर सकते हैं? यहाँ पर डिलीवरी की ऑप्शन नहीं है जी, यहाँ पर डिलीवरी की फैसिलिटी नहीं, क्योंकि आपका एरिया डिफरेंट जोन पे है. तो यू कैन क्रिएट ग्राफ अकॉर्डिंगली टू दैट. कितनी कौन कौन सी नोड्स रीचेबल है, कहते घूम फिर के, कहते इस नोड में, इस घर में आप जा सकते हो, डिफरेंट हाउसेस में जा सकते हो, पर यहाँ डिलीवरी नहीं हो सकती, तो यहाँ पर हमारा पाथ ही नहीं है, इस नोड से वो नोड कनेक्टेड ही नहीं है, ये आउटर स्कर्ट्स पे है. तो इन दैट केस वी कैन टेक द हेल्प ऑफ BFS ट्रांवर्सल, कि कौन कौन से आपके लोकेशंस हैं वो वहां से रीचेबल हैं. तो इस ग्राफ में तो सारी रीचेबल है. देयर माइट बी सम लाइक दिस, जैसे अगर मैं बोलूं इस ग्राफ में इस डायरेक्शन में आ जाए, तो T विल नेवर बी रीचेबल इन दैट केस. अगर मैं T की बात करूं, R से दिस इज अ डिलीवरी बॉय और आपका यहाँ इस जोन से जाना है, तो R to S डिलीवर कर सकता है, R to V भी डिलीवर कर सकता है, R to अगर आपने R to W भी डिलीवर कर सकता है यहाँ से यहाँ, लेकिन W to T नहीं जा सकता अगर ये सपोज करो डायरेक्टेड ग्राफ में इस तरफ नहीं है, और इवन X में भी नहीं जा सकता. So it tells, BFS basically tells the reachability of the node. DFS no doubt it do tell the same. दूसरा आता है इसमें, ये आपको शॉर्टेस्ट पाथ बताता है, एक तरह का शॉर्टेस्ट पाथ मान लो या डिस्टेंस मान लो. पाथ यहाँ पर ये मान के चल रहे हैं कि हर जो वो है इक्वल लेंथ का है. यू कैन से हाउ मेनी होप्स आर देयर, कितने आपने जंप्स मार के वहां पे जाना है. वी आर एज्यूमिंग ऑल एजेस आर ऑफ सेम वेट, 1 यूनिट के सारे हैं. तो व्हाट इज द शॉर्टेस्ट डिस्टेंस, यू कैन से स्मॉलेस्ट डिस्टेंस, कि अगर मुझे R2 अगर मुझे S जाना है तो आई शुड नॉट ऑप्ट फॉर दिस पाथ, क्योंकि ये पाथ 2 लेंथ का बन जाएगा. आई कैन गो फ्रॉम डायरेक्टली फ्रॉम दिस टू दिस पाथ. इट गिव्स अ काउंट ऑफ दोज लेंथ्स ऑफ द पाथ व्हिच आर बीइंग देयर रिक्वायर्ड. मुझे अगर मुझे X पे जाना है तो मुझे कम से कम 1 2 3 और 4 नोड का मुझे पाथ लेंथ मुझे जाके फिर मैं X पे पहुंचूंगी. इफ आई एम ऑप्टिंग फॉर दिस पाथ 1 2 3 4 5, दिस विल लीड टू लॉन्गर पाथ. तो इम्प्लिसिटली मुझे वो स्मॉलेस्ट पाथ को निकाल के दे देता है. तो जब हम BFS निकालते हैं तो एक BFS ट्री भी जनरेट होता है, जहां से हम शुरू कर रहे हैं वहां से उसको रूट नोड मान के जितनी रीचेबल वर्टिसेस हैं वो सारी उस ट्री के अंदर आ जाती है. ब्रेथ फर्स्ट ट्री बोलते हैं. BFS वर्क्स बोथ फॉर डायरेक्टेड एज वेल एज अनडायरेक्टेड ग्राफ लाइक व्हिच हैज बीन शोन हियर. तो इसमें चलता कैसे, विल डिस्कस दिस वन बाय वन. तो BFS के लिए वी आर मेंटेनिंग अ क्यू डाटा स्ट्रक्चर. तो पहले क्यू का ये देख लो सिंटेक्स, आपने किया भी होगा. लेट मी जस्ट गो थ्रू दिस. ये एक क्रूड फॉर्म में सिंटेक्स है. सबसे पहले स्टार्टिंग वर्टेक्स को आप क्यू में डालो, जहां से भी आप शुरू कर रहे हो. यू कैन स्टार्ट फ्रॉम एनीवेयर. तो ओके, स्टार्टिंग वर्टेक्स आपकी है तो NQ फर्स्ट वर्टेक्स, जहां से आप शुरू कर रहे हो पहले उस वर्टेक्स को आप क्यू में डाल दो. जब तक क्यू खाली ना हो जाए तब तक आप एक एक करके क्यू से एलिमेंट निकालो, उस एलिमेंट को प्रोसेस करो. प्रोसेस मतलब व्हाटसएवर यू वांट टू डू फॉर विद दैट एलिमेंट. फिर उस एलिमेंट के जितने भी एडजेसेंट टू वेरिएबल्स हैं, से एडजेसेंट टू वाई हैं, एक्स के जो एडजेसेंट टू थे 1 है 3 है, जो भी नोड्स इसके बिल्कुल पड़ोसी देश हैं जो डायरेक्ट कनेक्शन में हैं, उन उन जैसे इसके आर के एडजेसेंट टू क्या है, एस एंड वी। आर एस के एडजेसेंट टू कौन सा है, डब्ल्यू। एस के एडजेसेंट टू आर और वी नहीं है। एस के एडजेसेंट टू का मतलब एस से निकलती हुई लाइन, तो एस के एडजेसेंट टू सिर्फ डब्ल्यू है। यहाँ पर जितनी भी एडजेसेंट टू वर्टिसेस हैं जो पहले क्यू में नहीं गई हुई, नॉन विजिटेड का मतलब जो पहले क्यू में नहीं गई हुई, उनको आपने क्यू में डालना है। तो ये प्रोसेस चलता जाएगा जब तक क्यू एम्प्टी ना हो जाए। इफ आई एम जस्ट गिव अ ड्राई रन फॉर दिस, आर को आपने डाला अंदर क्यू के अंदर, तो साथ में आपका ग्राफ भी बनेगा, एक ब्रेथ फर्स्ट सर्च आपका ट्री बन रहा है, तो इसको प्रीडिसेसर ग्राफ भी बोलते हैं। आपने ये पहले ही नोट डाली, उसके एडजेसेंट टू इसको निकाला, और जो भी प्रिंट करना है आर को प्रिंट स्क्रीन के ऊपर प्रिंट कर दिया, बीएफएस ट्रांवर्सल लेट इट बी। ये ट्रांवर्सल का डाटा है जो आपका आउटपुट स्क्रीन पे जा रहा है। तो आर क्यू में गया था, आर निकाल लिया आपने, उसके एडजेसेंट टू एस और वी को क्यू में डाला। एस और बी किसके कारण क्यू में गए थे, आर के कारण। तो यहाँ पर एक ग्राफ बन जाएगा, बीएफएस ट्री बन जाएगा। बीएफएस ट्री क्या करे, एस और बी हैव एंटर्ड बिकॉज ऑफ आर। फिर आपने एस को निकाला, स्क्रीन के ऊपर प्रिंट किया। उसके बाद एस के एडजेसेंट टू क्या है जी, कहते हैं एस के एडजेसेंट डब्ल्यू है। डब्ल्यू किसके कारण आया था, एस के कारण, तो डब्ल्यू आपने क्यू में डाल दिया। फिर वी को निकाला, वी को निकाल के प्रोसेस कर दिया, तो वी के एडजेसेंट टू कौन से हैं, कहते जी एडजेसेंट टू कोई भी नहीं रहे, कहते एस, कहते वो ऑलरेडी क्यू में जा चुका है पहले, कहते बस एक ही एस ही था, कहते सिंपल वी को निकाल के प्रिंट करवा दो। फिर आगे डब्ल्यू, डब्ल्यू के लिए डब्ल्यू को आपने स्क्रीन पे प्रिंट किया, डब्ल्यू के एडजेसेंट टू अभी टी पड़ा है, एस तो पहले जा चुका है, तो टी इसके नीचे आ जाएगा, टी। टी के बाद कहते हैं जब टी को डाला इसके अंदर, डब्ल्यू निकाल चुके हैं, फिर टी के एडजेसेंट टू कौन सा है, कहते जी एक्स, तो एक्स आप टी आपका प्रिंट हो जाएगा। जब बाहर निकालोगे इसके एडजेसेंट टू एक्स आ गया, तो एक्स को आपने क्यू में डाला, और फिर आपने क्यू से निकाला एक्स, एक्स के एडजेसेंट टू कहते कोई भी नहीं है एडजेसेंट टू इसके, है ही नहीं कुछ भी। तो जब क्यू एम्प्टी हो गई, स्क्रीन से बाहर आ गई, ये आपके आउटपुट स्क्रीन में आ गया, ये आपके आगे इसका ब्रेथ फर्स्ट ट्री। और इसके एक प्रीडिसेसर भी होता है, प्रीडिसेसर मतलब डब्ल्यू का पेरेंट कौन सा है, इमीडिएट प्रीडिसेसर एस। टी का अगर मुझे आर से मुझे एक्स पे पहुंचना है, तो पाथ कैसे बताएगा, एक्स इज द डेस्टिनेशन, एक्स का प्रीडिसेसर देख लोगे तो टी है, जिसके कारण वो अंदर आया था इसके इस ट्री में, रिप्रेजेंटेशन में क्यू में आया था, जिसके कारण टी ने बुलाया था, क्योंकि टी के एडजेसेंट टू था। टी का प्रीडिसेसर क्या है, डब्ल्यू, डब्ल्यू का प्रीडिसेसर क्या है, एस, एस का प्रीडिसेसर क्या है, आर। दिस विल गिव मी पाथ फ्रॉम फॉर रीचिंग फ्रॉम दिस टू दिस, एंड पाथ लेंथ इसकी सेम होगी 1 2 3 4। तो ये बता देगा 4 पाथ लेंथ है, अगर मुझे आर टू एक्स जाना है, जो सा मर्जी पाथ ले लो, तो शॉर्टेस्ट पाथ आपका 4 लेंथ का ही बनेगा। This too can happen for some tree, you may get different, this very this output may also be different, and this tree can also be different। लेकिन जैसे अगर मेरे पास दो वेरिएंट होते हैं, आर टू एस, मैंने एस और वी पहले डाला है, क्या पता आर के बाद पहले मैं वी डाल दूं फिर एस डालूं, तो वो ऑर्डर पे डिपेंड करता है। तो मैंने इस वी को पहले डाला, तो वी के कॉरेस्पॉन्डिंग क्या पता कोई और चीज डल जाए, डिपेंडिंग ऑन द ग्राफ। तो योर traversal may be different depending, because there might be some possible set of many options, this can be different, but distance हमेशा same रहेगा, r to s का shortest distance। Path may be somewhat of varying nature, this is not compulsory that you are supposed to write BFS tree until and unless it has been asked in the exam to draw this tree, only then you should write। So what this does, BFS main purpose is it gives you a shortest path in terms of edges, that is count of edges. If I'm assuming every edge is of one weight each, so it give me the, let us suppose I want to go from R to X, it give me the shortest path in terms of count of edges, minimum number of edges. So it discovers what it says. If I want to find the shortest path, first I have to find, it will first find all the shortest paths starting from given source vertex with the distance k, then it will find the shortest path with distance of k plus 1. It goes step by step. Say first it finds the shortest path with all the nodes with this edge unit of 1, then it finds the, like in this case edge unit is 1, first v and x are being explored, then it finds the distance for w, here w is 1 plus 1, 2 distance, then it finds the distance from r source vertex r to t, that is 1 2 and 3, then it finds last distance of 4 unit, that is 1 2 3 and 4, the distance from r to x. So this works for both directed as well as undirected graph. The main application of BFS is to find the shortest path for the non-weighted graph. That means no weights has been assigned. If you want to find the shortest path in terms of count of edges, then this is the best option, BFS. We have started discussing this concept. What are the main crude steps of this? So what were the steps? That we will be first enqueuing the starting vertex. From wherever you want to start, you can enter that. That will be given to you in the paper also. Enqueue that and keep on dequeue that element while queue is not empty. Iterate over these steps, and which are the adjacent to vertices, enqueue all those adjacent vertices in the queue. Repeat this task until queue is not empty. If I just go for this one, so in this example we are just writing enter q. In the queue we entered r, then we remove the r and printed whatsoever you want to do, and then we visited all the adjacent to vertices. Now this is adjacent, v and s both are adjacent to, and now va and s, let us suppose initially s is being inserted, then v is being inserted inside the queue. After that s is being removed, and what are the vertices which are adjacent to s, that's w, that is inserted into the queue. S is being removed and processed. Now this is the traversal which is being printed on the screen. Then after that V is being removed, at any vertex which is adjacent to V, that is being added into the queue. Now we are left with no unvisited vertices. Now V adjacent to V, that node is S, which has already been explored and added to the queue, and now it has been printed. Now we are left with no other vertices. Then we will merely print this vertex and keep it out of that queue and just print it. Last we are remaining with W vertex. So W will be printed and its adjacent to will be added to the queue. Adjacent to of this is T. So T is added to the queue. And from T, when T is coming out of the queue, its adjacent to is added to the queue. And at the last X, X doesn't have any adjacent to, your system will just say remove the X element from the queue. So this is the traversal, BFS traversal, and this is a tree which has been generated because of that traversal. That this implicitly says that X is basically 1, 2, 3, 4, 4 units or edges apart from the source vertex, whereas W is just 2 unit at a distance from the source vertex. So this implicitly gives me the shortest path in terms of the count of edges. That is BFS. BFS can work both for directed as well as the undirected graph. If you go from the implementation point of view, here we are taking a help of adjacency list. I will tell you about adjacency matrix also. Both can be tried one by one. It hardly matters. What we have to do here, there are three things which are being used in this. There are three colors: white, gray, and black. White is if the that node is still untreated or undiscovered. Gray is once it enters into the queue, then this color changes to gray. When it comes out and this value is printed on the screen or nothing is left for that to be explored, then that is given the black color. Initially, all the vertices are being white color. Then there is called predecessor of the vertex. Predecessor means the node because of which it has entered into the queue. Like in this example, if I say for the how this said for with respect to W node, when you are saying W comes out of the queue and its adjacent to is being entered into the queue, and that is T. Now, what is the predecessor of T? That is W. Because of W, it has entered to the into the queue. So this its predecessor will be that of W, because W has made this vertex T to come inside. So we say predecessor of T is W. Because of T, this has predecessor of because of W, it has entered into the queue. So predecessor is there of the vertex, and source vertex from where you are starting, that is predecessor will always be equal to nil, because it is a starting vertex and no vertex was responsible for this vertex. And distance of the source vertex, which is computed from the algorithm, the distance of, if I say distance of x, d of x, distance of x will be equal to 1, 2, 3, 4 from the source vertex. Distance of w will be equal to that of 2. That distance is being implicitly being calculated here. And within the queue, all the vertices will be of gray color. Now coming up to this example, first of all, later on discuss the algorithm part. So what is inside this? Initialize all the vertices to white color, and we are starting with the S as a starting vertex for this case. This is the basically gray shade color. So we'll initialize it to gray shade because it has the first vertex which will be entered into the queue. Once it is entered into the queue, will settle it as a gray color. Its distance from itself, because it's a source vertex, distance from itself is 0. It doesn't have any predecessor, rather all the predecessors nodes of, for every node predecessor is initialized to nil, and distance for all the nodes is initialized to infinity other than that of the source vertex only. Other than source vertex, or rest of the values are initialized, the distance is equal to infinity. So what will happen? First of all, this we will find that from the adjacency list, the adjacent to nodes. Let us suppose this is the adjacent node, first one which is explored for the given source vertex S. So we will be settling down its color to gray. Along with that, let us discuss this one by one. That first will dequeue the vertex. The dequeue vertex is S, and adjacent to vertex of this is say R. First of all, R is being there, and we'll settle down the color of this as gray, and the distance is incremented by 1 unit of that of this. That distance of R will now become equal to 0 plus 1, that is one added distance, that of the previous vertex. This is U, this is V. So this color will become equal to gray. So accordingly, this value will be settled down, and the predecessor of this node R will become equal to S. That is predecessor of this V. This is U. Predecessor of this V will become equal to U. That is equal to S. These are the steps which are to be followed for this BFS traversal. So next, after for S, the next one more vertex which is left to be explored, that is W. For W, again check V color. Now this is the U vertex according to algo point of view. This is vertex V if I using the notations of this algorithm. So V is another vertex. This is basically W vertex. Its color is white. Yes, its color is white. Settle down this color as gray, and the distance of this will be U dot distance plus this. What is the U dot distance? That is the distance of S. 0 plus 1, that is S. Who is the predecessor of W? That is S. Because of S, it has entered into the queue. Similarly, we can settle down rest of the values. Now after this, once you are removing, the next element to be removed is R from the queue, because R and W has been entered. Now go for the adjacent to of R. Adjacent to R is S, which is already of gray shade. The like adjacent of 2 is R, with S, which is already of gray shade. We will explore now V vertex, which is still white. So again, V, what will happen? V will become of gray color. V predecessor will become equal to R, and V distance will be R distance plus 1, that will become equal to 2. So in this manner, you will be getting your V as gray color, distance is R. And then next, W is being popped out from the this queue. It is being dequeued from the queue. And for W, you now go for the adjacent to. Adjacent to this is this has become equal to once all the nodes of that S in we were starting with the S node. All the nodes have been processed. We have to settle down it as black. We'll discuss later on how to get it done. So if all the nodes of that node have been processed, we settle down that node as black. Now if you go for S, once S has earlier, if you see in the previous slide also, for S we have explored R and W both, and they have been entered into the queue. R was also gray shade now because it is inside the queue. W is also gray shade. Every tidbits have been settled down. After that, we have to mark this once it comes out from this if statement. With respect to the node adjacent to of S, we'll be making the S dot color as black. So this will be become black color like this here. So similarly, moving further, we can go for explore for R and W and so on. And we can keep on trying this practice. If you have got doubt, you can ask. These are the basic crude steps. That means first you will dequeue. For every dequeue value, we will finding the adjacent vertex of that. If that adjacent vertex is a white color, we will settle down as gray, and will adjust the distance accordingly. That is the distance of its predecessor plus 1. And for that node predecessor will be the U, which was being responsible for making that node inside that queue, and enqueue that value. And once all the nodes adjacent to U have been processed, then U will be settled on the color as black. So similarly, if I take this example for W node S, T and X are the adjacent two nodes. Now S is already black color. We have to explore only the white color. Now the W here is now basically your node here is W, which is U. Now adjacent to U, the vertices are S, which is already not white color. No. Next we'll go for the adjacent to vertices T and X. Now for T node, which is already white, we will have to settle down it as gray, and its predecessor distance will be that of distance of W plus 1. W distance is 1, 1 plus 1, 2. Its predecessor will be that of W. So in this manner, we will be updating these tidbits. Similarly, moving further for the X node, X is still white. If you are taking for the same W node, X will become equal to gray, and this is, distance will be that distance of W, which is already equal to 1, 1 plus 1, 2, and the predecessor value will be equal to W. Now this will be updated. Now, as we know that we have explored all the nodes of W, that means we have explored for the U value, that is W, we have explored all the vertices, that is S, comma T, comma that is S, comma T, comma X, that V values, all nodes we have explored, and we have enqueued all those value into the queue. Now we settled on W dot color as black. So W dot color will become equal to, now from gray this will be shaded as black color. So in the similar manner, we will keep on traversing these nodes because it is a connected graph and it is undirected one. So there is never a chance. We'll discuss one more tidbit inside this. So this will be keep on traversing all the nodes till all are coming into the category of black. So once you will getting this, or the queue is empty, implicitly all nodes will be processed for this. This may happen if your graph is disconnected, like this, these samples are there. In that case, you may not be able to traverse these subparts of the graph. Otherwise, all these nodes will be traversed by the BFS traversal. So moving further, this is a tidbit. Any doubt you can ask me for the same. In the same procedure will be repeated as we until your queue is not empty. In case your this graph adjoining graph, one more graph is being there, this is whole combination is called a single graph. These are some isolated vertices. We can say there are two connected component of the graph. One is this connected component and another is this connected component. BFS will be able to traverse only this connected component only. If we are starting from this node, it will be only able to traverse this part of the graph. So if for that, if you want that, we want BFS for traversal purpose, in that case, we will have to start, let us suppose earlier we started with the node S, then we have to let this node is say any node, say P or Q, we'll have to start from that remaining nodes also for traversing whole of the list elements of the graph. In that case, we will have to call BFS two times for the same. Now, one thing is possible that BFS traversal, multiple BFS trees are possible. That depends on the traversal. Now, in this example, if you see carefully this BFS tree for the same, you are starting from S vertex, then you did adjacent of R and W at some intermediate position. When you were inserting the inside the queue, the adjacent of W, in this graph, you firstly entered T, then you entered X. So adjacent of W is T and X. First you set the order, this as the first vertex you entered and this is the second vertex you entered. Based on this entry, once this T has been entered, so T will be coming out of the this queue. Once it coming out of the queue, its adjacent to, that is U, will be entered into the queue. So you will be traversed, you will not have any adjacent to. Similarly for X, when you are going for X, its adjacent to Y will be explored. That depends upon the order of the elements which are being entered into the queue. So depending upon the order, if for T and X they are entered, that BFS tree will be different. If for W, if I'm writing X and T for some graphs, your BFS traversal may be different one. So if both the outputs are correct, order does not matter inside this. The difference is on that output may be different, no doubt, but the shortest distance, if I say for the vertex Y, the shortest distance from the source vertex, it always remains the same. Like distance is 1 plus 1 plus 1. This is distance is 3. If I see this traversal technique, distance will be still equal to 3. So shortest distance from the source till the destination vertex, it is not being altered even if I change the order of the vertices. You may get different BFS. One student may get this output as BFS depending upon the order he has chosen. Another may get another output depending on the order he might have chosen in a different manner. So it both the answers are correct. You need not worry about the answers. Now let us sum up this BFS traversal. In this BFS traversal, what you are saying, initialize excluding the source vertex, all of the set of the vertices. For every vertex u belonging to whole of the vertices of graph, excluding the source vertex, we have done minus sign here. Set all the vertices to color as white, initialize, and distance is infinity, and predecessor of that is nil. This is the initialization mechanism. This will go for roughly order of v time because exactly v minus 1 vertices are being processed. One for loop is there. Then source vertex color is settled to gray color. That is the first vertex which is being added into the queue, and distance of its from itself of source vertex to itself is 0. Its predecessor is nil, and initially queue is empty, and we are enqueuing that source vertex into the queue. This chunk of operations will take a constant amount of time. Now you will be applying this procedure while q is not equal to nil, while q is not empty. You will dequeue an element, and for each adjacent element adjacent to that u element which you have dequeued from the queue, check if that color vertex is not visited yet, not discovered yet. If it is a white color, enter into the queue. Settle it as a gray color, enter into the queue, and set the distance of that is distance of its predecessor plus 1, and set the predecessor of that node as u node, and explore all these nodes for a given. That means this depends upon the number of edges associated with that vertex. So, and once you explore all the edges corresponding to that, settle that curve. Once all the edges have been explored for adjacent vertices have been explored, settle down the final color of that node as black. So this whole procedure, every time at least exactly one element will enter into the queue. That depends on the all the vertices one by one it will enter into the queue, and approximately for a given vertex, adjacent to vertex will be total set of edges. So what is the complexity of this chunk of code? That is order of v plus e basically. For v edges plus e times further to explore all the adjacent to vertex. This is for e times, and this will work for every vertex v. So a rough approximation time for this BFS traversal is v plus e if you are using adjacency list. If you are using adjacency matrix, in that case it will go for v square time, because for given vertex v you will have to explore again. If I want from adjacent to for given vertex v, you have to explore all the column entries for that, and if for given vertex v again you have to search for all the column entries where one is being there. So it will go for v square steps if you are using adjacency matrix representation.